In this lecture, I will give some background on linear programming problems and describe their solution using Mathematica. Linear programming is the name given to optimization problems of a special kind in which the function to be maximized or minimized, so-called objective function, is a linear function of the unknown variables, and where a certain number of constraints, either inequalities or equalities, acting between the unknown variables are also all linear functions. That description, while accurate, is a little hard to visualize, and so to visualize what that means, it's good to think of an example with just two variables. So imagine that you have a function of two variables, which is a linear function that you're trying to find a maximum or a minimum of. So with two variables, you can actually plot the function as a height function above a plane of the two variables. And here on the left, I've done that. The objective function, this f of x1, x2, is simply a tilted plane at some height above the x1, x2 plane. And so without some set of constraints to specify a region in which we look for a maximum or a minimum, there's no obvious maximum or minimum of this function, because you could make it be bigger by running off to the upper right corner, or smaller arbitrarily by running off to the lower left corner as far as you wanted. So consider the plane x1, x2 of possible values of the variables, here indicated by the first graph on the right. If we start having constraints that these variables have to satisfy, then it cuts down on the region in which we might look for a solution. So for instance, the dashed line in the first graph on the right there in the upper row defines, let's say, an inequality, so that below that line, along which x1 plus x2 is some constant, for example, so if x1 plus x2 is less than that constant, then the inequality will be satisfied, and that will be a valid region in which to look for a minimum, let's say, or a maximum of the function f, whereas above that dashed line it won't be satisfied. We might have more inequalities corresponding to further dashed lines, as shown in the lower left graph, each of which specifies a constraint on the region in which we can look for possible solutions. If the constraints are all inequalities here, then every single one of them says that the solution must be on one side of the line and not the other side. So for example, the vertical dashed line parallel to the vertical axis there amounts to the constraint that x2 has to be positive, and the horizontal dashed line along the horizontal axis amounts to the constraint that x1 has to be positive. And if the other three dashed lines are all requirements that the solution be on the consistently lower or left-hand side of those lines, then you have a region of possible solutions, which is this blue polygon. So now imagine that that blue polygon was sitting in the plane underneath the objective function, which is, if you like, a tilted orange plane above the blue polygon. And now you can begin to see that if, for example, you wanted to maximize the function, that you really only need to look at the corners of the blue region, because along any line which is an edge of the blue region, the orange objective function is either going to be tilted up or tilted down. In other words, if you run along that line, you'll either be going, if you run along the edge of the blue region, you're either going to be steadily increasing f or steadily decreasing f, and so when you come to the corner along that edge, it will be as big or as small as it can be. So if you're trying to make f bigger, then you're going to be probably looking at those two upper right corners of the blue polygon, and if you're trying to make f as small as possible, pretty clearly you're going to want that lower left corner. But in any case, the corners will be the places where the solution will be found. And that's because the objective function was a plane, and because the constraints were all linear inequalities. Now, we can visualize this situation with two variables and one objective function which is a plane that lies above it. We can't visualize it quite so easily if we have many variables, but it is still true that the region of possible solutions defined by some inequalities is a kind of polygon in n dimensions, and that on the corners of that polygon the solution is to be found. And it's because of this that linear programming is a special kind of optimization that's a lot easier to do than general optimization problems where we have some nonlinear function in some region that we're trying to optimize. Linear programming, there is an algorithm, it's called the simplex method, which is guaranteed to find the solution by, in a systematic way, looking along the corners. So that geometrically is what's going on in linear programming. Let's look at a specific example and how we represent it and solve it in Mathematica. So as I said, linear programming, as it says here, is a method to optimize some outcome, to maximize profit or minimize cost in some operation, in a circumstance in which the function that says what the profit is as a function of the things that you can vary, inputs to some plant, so that profit is a linear function of the things that you can vary, and that all of the constraints on the things you can vary are also linear functions. And if that's true, then the linear programming problem can be expressed as minimizing some vector dotted into a vector of variables x, some vector c dotted into a vector of variables x, subject to some matrix dotted into the same vector of variables being less than some vector, and typically the values of the vector of variables all being positive, as is usually the case. This is still pretty formal, and so let's consider a specific example. So we have a plant, and here's a plant diagram, and this is a very simple sort of plant where you have a single feed F, you have 3 reactor units, A, B, and C, and they're not identical. They were built, let's say, at different times, or they have different efficiencies. They produce some product, actually some pair of products, P1 and P2, and what we have to decide is how much feed to send to each of these 3 units in order that this plant be as profitable as possible in producing the P1 and P2 and using the F. So how do the units differ? Well, they have a different yield of the 2 products P1 and P2. Unit A yields 40% by weight of P1 and 60 of P2. Unit B yields 30% by weight of P1 and 70 of P2, and Unit C 50-50. And the feed costs 40 cents a pound. The product P1 is more valuable than P2. It's worth 60 cents a pound, and the product P2 less valuable, only 30 cents a pound. So you can imagine that you might want to feed the unit first that produces the most P1 and feed those units that produce less of the P1 and more of the P2 with lower priority. So that's the qualitative expectation. How can we find that out? Well, so here are the rules about the plant. We can't feed it more than 10,000 pounds a day, so the sum of the 3 feeds, FA, FB, and FC, have to be less than 10,000. Each of these 3 units, A, B, and C, has a limit to how much feed it can take. Otherwise, we would just give all of the feed to the unit C, which produces the most P1. Each one of them can only take 5,000 pounds a day. Also, we can't sell because of marketing limitations, let's say, more than 4,000 pounds a day of P1, and we can't sell more than, that's a typo there, that $, more than 7,000 pounds a day of P2. So this is a word problem, clearly, and we have to translate these statements into equalities and inequalities. So that's basically the job, is to write an objective function, the thing which we want to maximize here or minimize, which is the profitability of the plant, the amount of money made per day, and subject to these different constraints. So how do we go about making that translation? So the first thing we have to do is to identify what are the unknowns in the problem. What are the things that we want to find that we don't know? So we don't know fundamentally how much feed to give to A, B, and C, and we also don't know the total, although clearly the total is in terms of A, B, and C, FA plus FB plus FC. So we may say we don't know F, we don't know FA, we don't know FB, we don't know FC, and we don't know P1 and P2 either. So those are the things we don't know that we'd like to find out. And we want to combine them into a vector x of unknowns, and we need to decide on some order to write them and then be consistent about it as we go along. So here I've taken the order to be F, FA, FB, FC, P1, P2. Those are the entries in the vector of unknowns x. So what are we trying to optimize? Well, the profitability of the plant is what we're trying to maximize. The linear programming problem canonically is written as minimizing something. So if you want to maximize the profit, what you want to do is minimize the negative of the profit. So we write the profit then as being the value of the product minus the cost of the feed. So the products were P1 and P2, and they each have their price of 60 cents a pound and 30 cents a pound, and the feed has a price of 40 cents a pound. So the profit then is 0.6 P1 plus 0.3 P2 minus 0.4 F. And because of the order in which the variables here are written, that was a choice that we made, then the vector C, which if dotted into X will give minus the profit, is minus this vector here. So minus 0.4 because the feed term comes in with a minus 0.4, and that's the first of these variables. Plus 0.6 in the next to last entry because the next to last entry is P1, and the profit has a term 0.6 P1, and the final term being 0.3 times P2 because this P2 is the last entry, so there's a 0.3 here. And the variables that are not mentioned here, FA, FB, FC, are 0. We don't need to know what those values are to compute the profit, just the total feed. So having decided on the unknowns and the order in which they appear in the vector x, and having written the cost function and therefore figured out the vector c, the next thing we need to do is to write the constraints which have to be satisfied by any valid solution to the problem. So there's two different kinds of constraints here. There are equalities and inequalities. So the inequalities that were stated above, if you go back and read the word problem, is that the total feed has to be less than 10,000 pounds a day, that the feed to each unit has to be less than 5,000 pounds a day, so FA, FB, and FC are all separately less than 5,000, that we can't sell more than 4,000 pounds a day of P1, and we can't sell more than 7,000 pounds a day of P2. The equalities that the solution must satisfy are, first, that the total feed is the sum of the feeds of the three units, F is equal to FA plus FB plus FC, and then that the total amount of P1 that's produced, it's produced by each of the three units, and they each had their own efficiency in terms of the feed. So for example, the first unit produced 40% P1 and 60% P2, and so that means then that the P1 has a term 0.4 times the feed to A, and P2 has a term of 0.6 times the feed to A. That's the contribution of the A unit to the amount of P1 made and the amount of P2 made. And similarly, the contribution of the B unit is 30% times its feed is P1, and 70% of its feed is P2, and likewise C produced 50% P1 and 50% P2. So that's the form then of the total production of P1 and the total production of P2 in terms of the feeds to each unit. Now we could have not taken f as a variable, and then we would have had not this equality, but we would have written this one here and said that fa plus fb plus fc was less than 10,000, and then we would have had that the profitability vector would have had a 0.4 times fa plus fb plus fc, so each of these three values would have had a 0.4, and there wouldn't be a first value, and that's a choice. Sometimes in linear programming problems you can either keep a quantity as a variable and then have an equality which relates it to others, or solve for it beforehand, and that's just simply a choice for convenience. So that's translating the word problem into a set of equations, and now we need to solve it, and for this we use Mathematica's function called linear programming. And the whole problem here is basically to translate these equations into input that Mathematica can understand. The form that we want is the second of these various forms, because we have some of our constraints that are equalities and some that are inequalities. And so the syntax of this, as written here, is a little bit complicated, and that's why we have this example here to guide us as to what sort of input to give to Mathematica. Basically, we need to tell it the vector c, which was used to define the function we want to minimize, the matrix M, which is the left-hand side of the constraint matrix, and then the set of right-hand side values of the constraints together with a little flag, a value which is either 1 or 0 or -1, depending on whether this is an inequality which is a less than, an equality, or an inequality which is a greater than. We'll see how that works in just a minute. So first, the cost vector. Well, we just wrote that out up here, and so we simply write that in Mathematica language using curly brackets to make the list, and it's the very same set of numbers in the very same order. Next comes the matrix, which I've called A here for some reason, matrix of the set of rows which define the different equalities and inequalities. And so I've got first a set of the rows which all correspond to the inequalities. And each one of those only mentioned one variable, f, fa, fb, fc, p1, p2. Every single one of the variables in our list of unknowns, in this case, has an inequality. And so they all appear here as a vector with only one entry, because this will be the way that we access f in order to write an inequality on f. This will be the inequality on fa, this will be the inequality on fb, and so forth. The right-hand sides of those are the list here B. So it's a list of pairs, and the first entry is the right-hand side of the inequality, and the second is a flag which tells you whether it's less than or greater than, or if it's 0, then an equality. So because this was f is less than 10,000, then this first pair is 10,000, comma, -1. The next one says FA, which was the second variable, is less than 5,000. So again, here it's 5,000 that it's less than. Here's FB, which is likewise less than 5,000. Here's FC, that's the fourth variable, which is less than 5,000. Then there's P1, which is the fifth variable, and that's less than 4,000. And then there's P2, which is less than 7,000. So it's really important in writing these things out to have written down someplace so that you know what it is, the order of the values in your vector of variables. And you are the one who's responsible for deciding that, and you need to be consistent about it as you go along. So those are the inequalities. And then we have, in addition, three equalities, which, for reference, are right here. First, that f is the sum of fa plus fb plus fc. And the way we write that as an inequality is minus f plus fa plus fb plus fc is equal to 0. In other words, this vector dotted into the vector of unknowns gives 0. So this corresponding right-hand side is the 0 that it gives, and then another 0 to tell you this is an equality, not less than, not greater than, but strictly equal. This likewise is the expression for P1. So what it says is minus P1 plus 0.4 times FA plus 0.3 times FB plus 0.5 times FC strictly equals 0. That's what this has as a right-hand side. And this, as you can see, is what you get if you rearrange this equation to make it 0 equals this stuff here minus the P1. So the interpretation of these rows in the matrix A are the vectors that you would need to dot into the list of variables in such a way that you will give the left-hand side of the equality or the inequality. So in these cases, it's simple. It's just a vector with one element to pick off the proper value that you're trying to make an inequality. In these cases, it's more complicated because many variables are mentioned at once to define these equalities. So in this second one here, there's a 0.6, 0.7, 0.5 for the ABC, the FA, FB, FC entries, and a -1 in the very last entry for P2, and that is set to 0. So there's no mention of F, that was the first variable, but it's 0.6 FA, 0.7 FB, 0.5 FC added together minus P2 times 1, okay, equals 0. And this corresponding element in the B list is the 0 that it's equal to and a 0 that says this is an equality, not an inequality. So study this example carefully because this is how you translate the linear programming problem into Mathematica. So here's the matrix all written out pretty, and here's the matrix form of B. Solving the problem, once you have these three things, is just typing in linear programming vector C for the cost function, matrix A, list B for the right-hand sides, and asking for the answer. And then it tells you the values. And those values are the values of F, FA, FB, FC, P1, and P2 in the units of the problem. So it says total feed 8750, of which 5,000 goes to unit C, maxing it out. That's as much as you can put in. And remember, we argued that the expectation would be give all the feed you can to the most efficient unit, the one that produces the most of the high value product, and then feed the other ones in turn. And the reason that you don't feed the other ones the 5,000 that they could take is because eventually you max out the amount of P1 that you can produce, and then you don't feed those units anymore. I'm describing in physical terms what is the reason for the solution that you get. But this is what is produced by the linear programming simplex algorithm, which Mathematica is using when you use this function. You can then evaluate the profit at the optimum by taking this answer and dotting it into the cost function and remembering to change the sign, because this thing without the minus sign is minus the profit, i.e. the cost, and so minus that is the profit, which is 325 in some units or other. That would be dollars per day, I guess. Yes, because we were working in dollars and days. So that is how you do a linear programming problem using Mathematica. The first part of it is translating the word problem into a set of equations, a cost function, equalities and inequalities. The second part of it is transcribing those into the language of Mathematica, in which your first job is to figure out what order your variables come in, and then your second job is to find the vector for the function that you want to minimize, and then your list of vectors and right-hand sides that correspond to the equalities and inequalities. And then you basically just press solve.